In part 1 of lecture 3, we will discuss the responsibilities of the operating system. A computer's operating system is the single most complex piece of software to run on a computer. It is far more complicated than application software because it deals with so many things on so many different levels. It has to manage all the computer's resources and at the same time deal with the low-level details of managing physical devices. If you were to deal with all the amount of code needed to get a typical application to work, like a compiler for example, you would like fewer lines of source code with far less interaction among its components, and that the interaction with the hardware is shielded by several layers of software. All of this combines to make an operating system a very difficult project to design and whose implementation to manage. The operating system has to manage all areas of computer operations, managing processes, memory, the file system, I/O devices, disk drives, network services, as well as providing protection and a viable user interface. Given the complexity of an operating system, it should not be surprising that they differ in their basic structure. We are going to start with a look at the types of features that an operating system must include, and we will look at the different ways in which these can be organized. Harvey Deitel, in his classic text Operating Systems, gives several different definitions of the term process, which range from rather pedestrian to overly poetic. In essence, a process is the act of executing a program. It doesn't matter if the program is a batch job or running on a time-sharing system, or even if it is performing an operating system chore like managing the printer spool. Every instance where a program is being run counts as a separate process. If the same program is being run by two users, it counts as two processes. If the users on a system are running 3 editor sessions, 2 compilers, and a game of Hunt the Wumpus, that counts as 6 processes. It is important to keep in mind that all of these processes will need resources to run, including a certain minimum amount of memory, a certain amount of CPU time, various I/O devices, and so on. The operating system is responsible for the main events in the life of a process, creating and deleting them, suspending them when the system is overloaded or when the user requests it, and resuming them when the system's load is stabilized or when the user requests it. Additionally, processes need to be able to coordinate themselves with other processes with whom they may be sharing a larger task. This means that they have to be able to synchronize and communicate with each other. This is all handled for them by the operating system. Lastly, the operating system has to be able to detect and recover from deadlock when two processes are keeping each other from finishing its work by holding on to resources that the other process needs. This is a topic that we will look at in depth a little later in the course. All programs that hope to run on the system need memory. They need memory to store their executable code, and they need memory for data. Running a program means translating the addresses as they appear in a program into the physical address that the hardware will use to fetch and store data and instructions. These will typically differ. Most computers use a relocatable addressing scheme that uses the contents of one or two registers together with an offset to form the physical address. This makes programs easier to run because the operating system can now load them anywhere in memory without the user having to worry if it can find its own data and instructions. Exactly how this translation is performed depends on the design of the computer's memory management unit. When a process terminates execution, whatever memory is held must be freed and made available for other processes' use. Otherwise, we will eventually run out of available memory. Lastly, we must assume that multiple processes will be in memory concurrently. After all, this is true for most multi-user or multitasking systems. But it means that the restrictions on exactly what parts of memory can be accessed by any one given process must be tightly controlled. The operating system will have responsibility for keeping track of the parts of memory in use and which processes are using these. It must decide which process will be loaded into a given unit of memory when it becomes free. And it must allocate and deallocate memory as it becomes necessary to do so. Files are the logical organization that we give to data, although we associate a file with an input or output device, or perhaps a secondary storage device. Files exist on a different level from devices. Files exist in the realm of data and information, and the way in which we expect data to appear, the order in which we read it or write it, and whatever sense of organization or hierarchy we give to it, and all these help to define how we think of our files. Devices are hardware, and here we are directly or indirectly concerned with the details of hardware, registers, data representation, physical connections for power and data transmission, and so on. A file is defined by its creator as a collection of related data. The operating system's job is then to map it to its corresponding I/O or storage device so that it can be used by the system. The operating system is responsible for the life events of a file, including creating and deleting it, and the directory in which it is located. An operating system has to support the primitive operations used by systems and user programs for manipulating files and their directories. It has to be able to map files to the devices on which they are located. And an operating system has to be able to back up files onto non-volatile storage devices as necessary and as requested. All input-output devices have their own little quirks that make them different from other devices. These quirks show up in different ways. The control characters that they use, their register sets, and the instruction sets of their controllers, and so on. Users do not really want to deal with this. They want a uniform look and feel regardless of which I/O device they are using. The subsystem that controls the I/O devices includes the memory management for buffer caches and spoolers, and the device drivers. The drivers must include both the general routines used by all devices, as well as device-specific drivers that handle low-level tasks on individual devices. All computers have secondary storage. They have it because it is far too impractical to have enough memory to store all the computer's data and software in memory, and far too expensive. And even if it weren't, the fact that memory is usually volatile would make it a very bad idea. The operating system's job includes managing free space on storage devices, allocating it as needed, and scheduling disk operations as they come up. Distributed systems involve a set of processors that don't share memory, peripherals, or a clock. Usually, these are separate computers that are connected via a network. They communicate with each other, and they may share the use of each other's resources. A file server, a computer whose sole or primary purpose is to provide files and data to other computers in a network is an example of these shared resources. Frequently, the various processors may work cooperatively on a problem, dividing it into a series of smaller tasks. This requires that they communicate and synchronize what they are working on. The operating system is given the job of providing a means for the various stations on a network to communicate with each other. Usually, when file access is shared, the operating system will try to give the appearance that there is nothing different about files accessed via a network and files accessed via the computer's own disk drives. Systems that run more than one program or support more than one user at a time need some means of keeping each process or user from inadvertently stepping on each other's toes. This means providing some means of protection for the main resources of the computer, its memory, files, and I/O devices. Although different users can use memory at the same time, they obviously cannot share the same memory space simultaneously. Similarly, they can all use files and I/O devices, but not the same ones at the same time. This threatens the integrity of the data being used and generated, and this is not satisfactory for anyone using the system. Providing protection will require creating and maintaining a control mechanism for the system's various resources. When the average computer user thinks of the operating system, what they often think about is the user interface. In fact, most users really think that it is the operating system. But in reality, it is just the tip of the proverbial iceberg. The user interface is the software through which users interact with the computer, starting programs, copying files, and so on. In older systems, it was almost always a command interpreter, allowing users to type in a line and perform one operation or another, depending on the command typed in and the parameters that accompanied it. In even older systems, commands were punched on punch cards, with each card containing a different command. Currently, we expect computers to use a graphical user interface, where most commands are either menu-driven or represented by icons that can be clicked or dragged with a mouse pointer. Graphical user interfaces, or GUIs as they are more commonly known, come with a price tag. Graphical interfaces require more computing resources, including monitors with better resolution, more memory, faster CPUs, and more secondary storage. But if you ask the typical computer user, he or she would agree that it's worth it.